It's almost strange how quickly we forget the way things used to be. Just a couple of years back, whenever astronomers talked about galaxies in the farthest reaches of space, every statement came wrapped in uncertainty. We believed we had glimpsed the first generation of stars lighting up. We felt reasonably confident about the shape and structure of early galaxies. And as for planets orbiting distant stars, we were essentially working in the dark, piecing together hints and praying the data held up. Then the James Webb Space Telescope opened its instruments and began sending back images. Suddenly, all those uncertainties began to evaporate. We stopped merely detecting planets and started identifying what chemicals floated through their skies. We stopped squinting at smudges of light from over 13 billion years ago and started examining galaxies so fully developed, so intricate, that by every rule we thought we understood, they had no business existing yet. And that happened in just the opening months. Since then, James Webb has been systematically dismantling our models of the cosmos, one observation at a time. From galaxies that extinguished their stars billions of years before anyone expected, to molecular signatures in distant atmospheres that seem impossible without life. If you thought this telescope would gently confirm our theories, you couldn't have been more wrong. So let's walk through the timeline. Not the engineering marvels, not the launch hype, but the actual work. The findings that came one after another, each one forcing astronomers to reconsider what they thought they knew. Because the real story of James Webb isn't its mirror or its orbit, it's the flood of discoveries that keep arriving, many of which still don't fit into any framework we've built. Everyone saw that first image. It looked almost like cosmic wallpaper, nothing more than a speck of sky blown up beyond recognition. But once the initial awe subsided and people moved past simply calling it beautiful, the scientists began analyzing what was actually in the frame. That's when things turned strange. That single photograph revealed thousands upon thousands of galaxies. Not individual stars, not planets, but entire galaxies, each one containing billions of stars, all scattered across a patch of sky no larger than a grain of sand held at arm's length. The cluster itself was cataloged as SMACS 0723. A colossal gathering of galaxies sitting roughly 4.6 billion light-years away in the southern constellation Volans. But the name was almost irrelevant. What mattered was what the image demonstrated. For the first time, humanity possessed a clear infrared view into the deepest layers of the universe. And it wasn't just displaying distant galaxies in sharp focus. It was showing light that had been warped, bent into arcs, and stretched into ghostly curves by the gravitational pull of massive objects. That warping wasn't a flaw in the optics. It was gravity itself. Enormous clusters of galaxies in the foreground were bending the light from even more distant galaxies behind them. And those distortions weren't just visually striking, they were scientifically invaluable. Gravitational lensing functions, like a natural magnifying glass. It amplifies faint objects. It reveals details that would otherwise remain hidden. It lets astronomers peer behind the veil. And in that first image, scientists were already observing galaxies that existed more than 13 billion years ago, mere hundreds of millions of years after the Big Bang itself. That alone would have been remarkable. But what truly caught everyone off guard was how those galaxies looked. Some of them appeared far too bright, too organized, too evolved, and that didn't align with expectations. According to the dominant models, galaxies in that era should have been small, disorganized, still assembling their first generation of stars. Yet what Webb revealed, even in that inaugural photograph, was something far more advanced. Smooth structures, well-defined clusters, clear evidence of star formation that should have required hundreds of millions of years to develop, more time than the universe had even given them at that stage. So naturally, the questions started piling up. Were these galaxies somehow forming at a pace we didn't think was physically possible? Were our cosmological models fundamentally flawed? Or were we witnessing something entirely different? A kind of structure that assembled under rules we hadn't yet written down. And this was just the beginning. Before Webb had even completed its full calibration, before its suite of instruments had been tested across the full spectrum, it had already forced cosmologists back to the drawing board. Not because the data was unclear. On the contrary, it was too clear. It didn't support the predictions. It challenged them head-on. What's especially striking is that this wasn't the result of some painstaking multi-year survey. It was a snapshot, a brief glimpse, proof that even in the emptiest regions of the sky, there are entire cosmic histories hidden in the darkness. silent and unseen until the right instrument finally arrives. That instrument was James Webb, and within hours, it had redrawn the map of the early universe. But a telescope like Webb wasn't constructed solely to peer into the ancient past. It was also engineered to examine objects much closer to home. Not galaxies billions of light years distant, but stars in our own neighborhood, stars with their own collection of orbiting worlds. Worlds that humanity has been chasing for years, estimating their sizes, guessing at their temperatures, watching their silhouettes pass in front of their host stars, and until recently, that's all we really had. Silhouettes. When a planet crossed in front of its star, astronomers would detect a tiny drop in brightness. That's how exoplanets were discovered. That's how they were measured. The technique worked, but it was limited. You can learn something from a shadow, but it doesn't tell you what the planet is made of. It doesn't reveal what gases hang in its atmosphere, or whether anything might be living there. Webb changed that equation. Its infrared sensitivity made it possible, for the first time, to directly read the chemical fingerprints embedded in an exoplanet's atmosphere, not indirectly through statistical modeling or buried in noise, but directly by splitting the light that filtered through the planet's atmosphere and analyzing the spectrum wavelength by wavelength. That's how scientists obtained the first unambiguous detection of carbon dioxide on a planet beyond our solar system. The planet, WSP-39b, a scorching gas giant 700 light-years away. That single result validated the entire concept. Webb wasn't just hype anymore. It could genuinely read the atmospheres of alien worlds. And then it went further. Webb detected water vapor on WSP-18b, WSP-80b, and GJ-486b. These aren't hospitable planets by any stretch. One is boiling. Another practically skims the surface of its star. But the significance isn't whether they could support life. The significance is that astronomers could read them, measure the density of their clouds, track fluctuations in atmospheric pressure, identify gases like methane and sulfur dioxide, molecules that carry meaning when they appear in specific combinations. Then came the observation of WSP-17b, and that's where things took a bizarre turn. Webb didn't just find vapor or familiar gases, it found solid particles floating in the planet's sky, tiny silicate crystals, essentially microscopic quartz, suspended in the atmosphere like fragments of glass drifting through the air. The same way Earth's clouds carry water droplets, this distant world was circulating shards of mineral through its atmosphere, like some kind of alien hailstorm. It was the first time anything like that had been observed. And it forced a realization. Exoplanets don't play by Earth's rules. Their weather systems, their atmospheric dynamics, their entire chemical logic might be radically different from anything we've experienced. Wildly, unpredictably different. And Webb was the first instrument with the resolution and sensitivity to actually show that. But the telescope didn't limit itself to exoplanets. Webb also turned its gaze inward, toward targets within our own solar system. And even though these objects were far closer, Webb still managed to deliver surprises. It captured the sharpest images of Neptune in over 3 decades. Not just the ring system, but thermal profiles of the poles, fine structure in the cloud tops. The level of detail was unprecedented. Then it focused on Chariklo, a peculiar asteroid with its own miniature ring system, and detected water ice on its surface. That's an object only a few hundred kilometers across, yet Webb could map its composition with precision. Then the telescope locked onto Europa, one of Jupiter's moons, and detected plumes of water vapor erupting into space. This confirmed suspicions raised by older missions like Galileo and Hubble. But this time, the data was crystal clear. Europa wasn't just a frozen shell. It was geologically active, venting material from its hidden subsurface ocean like a slow leak in the ice. And Webb was watching it happen in real time. Even a small comet, 238P, Red, a minor rock drifting through the asteroid belt, received attention. Webb detected water vapor, but no carbon dioxide, which struck researchers as odd. Most comets contain both. This one didn't. That discrepancy offers clues about where the comet originally formed, perhaps in a warmer region of the early solar system, or it suggests that its carbon dioxide sublimated away long ago. Either way, it's a piece of evidence about comet origins, about the chemistry that shaped our solar system, about how water eventually reached Earth in the first place. And then there were the trans-Neptunian objects, icy remnants drifting far beyond Pluto's orbit. Webb started detecting traces of methanol and organic compounds on these distant bodies, helping scientists reconstruct what the outer solar system looked like in its infancy. These weren't just inert leftovers. They had chemistry. They had history. They had stories written into their surfaces. So yes, James Webb was built to look far, but it proved equally powerful when it looked close. Because every time it examined something astronomers thought they understood, whether it was a planet already cataloged or a moon humanity had been orbiting for decades, it revealed something new, something overlooked, something that changed the picture just enough to matter. Throughout 2023, JWST began delivering data from its deep field surveys, and one of the first things that became apparent was the sheer density of galaxies appearing in the first few 100 million years after the Big Bang. Not faint smudges of background light, not statistical noise, but fully realized galaxies. Dozens at first, then hundreds, in regions astronomers had assumed were still largely empty. And some of them were fundamentally wrong. Take Sears 93316, for example. Based on its redshift, this galaxy appeared to exist just 235 million years after the Big Bang. At the time of its identification, it was the most distant galaxy ever observed. That's far earlier than anyone expected to find anything that complex. And it wasn't an isolated case. Webb kept finding more like it. Bright, compact, highly structured galaxies that didn't look like they were still assembling. They looked finished. And that posed a significant problem, because building a galaxy like that requires time. It requires heavy elements. It requires generations of stars that live, die, explode, and seed the next generation with their remnants. It requires dust, gas, rotation, gravitational stability, all working in coordination over hundreds of millions of years. But these galaxies didn't have that kind of time, so something in the model wasn't adding up. Were these galaxies somehow forming faster than any mechanism previously observed? Were they forming through entirely different processes, bypassing steps astronomers thought were essential? Or was the entire timeline for the early universe off by a significant margin? And then Webb found something even more unsettling. The JWST Advanced Deep Extragalactic Survey, known as JADES, one of its most extensive deep field imaging programs, focused on two specific regions, called GOODS South and GOODS North. These observations were intended to refine understanding of galaxy formation and clarify how supermassive black holes could achieve such enormous masses so early in cosmic history. However, a surprising discovery from JADES data challenged one of the foundational assumptions about the universe's structure, specifically the principle of isotropy, which holds that the universe should appear roughly uniform in all directions, with no preferred orientation or inherent spin. In a study led by Lior Shamir of Kansas State University, researchers analyzed 263 spiral galaxies in the GOODS South field using an algorithm called Ganalyzer, which determines galaxy spin direction from radial intensity plots. The results revealed a striking asymmetry. 158 galaxies, roughly 60%, rotated clockwise, while 105, 40%, rotated counterclockwise. This imbalance hinted at a possible preferred spin direction in this region of space, challenging the assumption of a directionless, homogeneous universe. Previous studies had noted similar spin asymmetries, with the effect appearing more pronounced at higher redshifts, suggesting a potential primordial structure embedded in the cosmos. Some researchers speculated this could align with physicist Nikodem Poplawski's unconventional theory, which proposes that our universe formed inside a rotating black hole within a parent universe, possibly imparting a directional spin bias to cosmic structures. However, Shamir's team offered a more conventional explanation. The asymmetry might stem from a Doppler effect bias. The Milky Way's motion through space could make galaxies spinning opposite to our perspective. Appearing clockwise from Earth seems slightly brighter due to blue shift potentially skewing automated classifications. The relatively small sample size of 263 galaxies and the inherent challenges of imaging faint high redshift objects urged caution. Larger, more diverse datasets from ongoing JWST observations would be crucial to determine whether this asymmetry reflects a true cosmic phenomenon or simply an observational artifact. Compounding these challenges to cosmological models, JADES also uncovered galaxies with redshifts exceeding 13. meaning they existed when the universe was less than 330 million years old. These galaxies, far from being weak protostructures, were luminous, compact, and surprisingly mature. A standout example, JWST Z130, with its extreme redshift, forced astronomers to reconsider how early galaxies could collapse from primordial gas clouds in such a compressed time frame. Typically, such collapses require extended periods. Yet these galaxies appeared fully formed within the universe's first 300 million years. This wasn't an isolated anomaly. It was part of a pattern. These early galaxies weren't just existing passively. They were thriving, actively forming stars at absurd rates. More stars than they should have been able to produce with the limited raw materials available at that time. It was like watching a campfire suddenly erupt into an industrial blaze, except in the vacuum of space, before the fuel had even dried. Some astronomers began calling it the too early, too big problem. The galaxies were too massive, too luminous, too soon. So what could explain it? One possibility is that star formation in the early universe was simply more efficient than current models predicted. Maybe conditions back then, higher densities, more frequent galactic collisions, allowed galaxies to accelerate their growth at previously unimaginable speeds. Or perhaps our models are missing some critical ingredient, a cooling mechanism, a gravitational feedback loop, something fundamental that hasn't been accounted for yet. Another idea gaining traction is direct collapse. Instead of slowly accumulating stars and building mass over time, maybe some galaxies collapsed almost instantly from dense gas clouds, forming stars and black holes in one chaotic, explosive event. If that's accurate, it could also explain how some of the earliest quasars, those incredibly bright beacons powered by feeding black holes, managed to exist so early as well. But here's the twist. The more astronomers try to explain it, the more complicated the picture becomes. Because every time Webb stares into those early epochs, it finds more galaxies, not fewer, more light, not less, more structure when randomness was expected. And now astronomers are confronting a deeper question. What if the early universe was never as quiet as models suggested? What if everything, stars, galaxies, black holes, ignited faster and louder than anyone ever imagined? If that's true, then the universe isn't just older than we thought. It's more aggressive, more dynamic, more alive, even in its infancy. And all of this, every one of these findings that shattered the timeline, came from just the first year of Webb's deep field observations. The surface has barely been scratched. Astronomers barely had time to process those early deep field surprises before another, even more unsettling question rose to the surface. If these galaxies were already so massive, so bright, and so well organized in the universe's opening chapters, then what about the objects that usually grow in lockstep with galaxies? Black holes. Most large galaxies in the modern universe host a supermassive black hole at their center, sometimes billions of times the mass of the Sunday. But how those monsters came to be is still one of the most stubborn mysteries in astrophysics. Do they begin as ordinary stellar mass black holes, formed from collapsing stars, that then take billions of years to gorge themselves into giants? Or do some of them form already huge, born from catastrophic collapses on scales never directly observed? James Webb didn't answer that outright, but it did something arguably more disruptive. It showed that actively feeding black holes were already in place in the early universe, at epochs when, according to our best models, they shouldn't have had time to exist. One of the most striking examples came from a distant, faint galaxy cataloged in an early deep survey. When Webb's instruments probed it more carefully, the data revealed a signature that was impossible to ignore: an active galactic nucleus. At the center of this young galaxy, a black hole wasn't just present, it was devouring matter, heating up its surroundings, blasting out radiation, and this was happening when the universe was only a few 100 million years old. That poses a brutal timing problem. To grow a black hole, you need ingredients. You need stars to form and die. You need dense regions of gas that can collapse and feed the core. You need time for matter to spiral inward and cross the event horizon. Yet there, at an epoch when the universe was barely out of its newborn phase, sat a black hole bold enough to announce itself across billions of light years. It hadn't just formed, it had grown. This pushed astronomers back toward an idea many had treated as speculative: direct collapse black holes. Instead of starting as small remnants of stars, perhaps some black holes emerged directly from enormous clumps of gas, collapsing under their own gravity before any star had a chance to ignite. In such a scenario, a cloud hundreds of thousands or millions of times the mass of the Sun could bypass star formation entirely, collapsing straight into a black hole. It would be messy, it would be violent, but it would also explain how some black holes could be born big. Once a black hole starts out massive, it doesn't stay quiet. It becomes a quasar, an object so bright that its light can overpower the combined starlight of its entire host galaxy. Webb began picking out quasars whose light had been traveling for over 13 billion years, their glow distorted and magnified by intervening galaxy clusters. In some cases, gravitational lensing turned these otherwise unreachable objects into cosmic close-ups, stretching their light and giving astronomers a rare chance to study them in detail. Lensing turned out to be more than a clever trick of gravity. It became a kind of natural time machine. A dramatic example came from a supernova whose light was split and bent by a massive cluster, causing the same explosion to appear in multiple positions on the sky, each image arriving at a slightly different time. From our vantage point, it was as if the universe had replayed the same cosmic event 3 times, delayed by the different paths the light had to take. This wasn't just a curiosity. By measuring those time delays and carefully modeling the mass distribution in the lensing cluster, astronomers gained a powerful tool to probe the expansion of the universe itself. For years, 2 primary methods of measuring the cosmic expansion rate have yielded conflicting answers. A thorny problem known as the Hubble tension. Lens supernovae offer a third, independent way to weigh in on that debate. Webb's ability to detect these events at tremendous distances means that, over time, it could help resolve one of cosmology's most persistent disagreements, or prove that the universe is hiding some deeper twist. But while Webb was busy uncovering black holes that seemed to form too early and explosions that could help measure the fabric of cosmic expansion, it stumbled into another surprise that challenged expectations in a different way. It started finding galaxies that had already gone quiet. In standard models of galaxy evolution, star formation is a drawn-out, occasionally chaotic process. Gas clouds collapse, stars ignite. Some explode as supernovae, others drift quietly through the ages. Over billions of years, feedback from stellar winds, supernovae, and black holes can eventually blow out or heat up a galaxy's gas, shutting down star formation and leaving behind a red and dead system, populated mostly by older stars. That's what astronomers expect to find in the mature universe. But Webb began detecting galaxies that appeared quiescent, no significant star formation, very little cold gas to work with within the first billion years after the Big Bang. These systems looked, in many respects, like elderly galaxies, at a time when the universe itself was still in its cosmic childhood. Their starlight suggested populations that had burned through their gas supply quickly and then abruptly stopped producing new stars. It was like walking into a kindergarten classroom and finding someone who already looked like they had lived a full lifetime. The data implied that these galaxies had experienced intense, rapid bursts of star formation early on, consuming or ejecting their gas in a short, furious blaze. Then, as if someone had flipped a switch, they quieted down. They are sometimes referred to as sleeping beauty galaxies, not because anyone knows if they will awaken again, but because they seem to have passed through their active phase so quickly that the universe barely had time to notice. This compounds the earlier too early, too big issue. Not only were galaxies forming faster and growing larger than expected, some of them were also shutting down their star formation far sooner than models allowed. Whatever was governing the flow of gas into and out of galaxies in those first few 100 million years, it was far more extreme, more efficient, or more chaotic than simple theories had predicted. For a while, Webb's most unsettling contributions centered around timing and structure. Galaxies forming too soon, black holes appearing too big, star formation turning on and off abruptly. But as the telescope collected more data, the focus began to shift from architecture to habitability, from the shape of the universe to the possibility of life within it. The transition became clear when attention turned to a particular exoplanet orbiting a relatively cool star in the constellation Leo. The planet, larger than Earth but smaller than Neptune, resides in a zone where temperatures could allow liquid water under the right conditions. Earlier telescopes had found ambiguous hints of water vapor in its atmosphere, enough to place it on the growing list of intriguing, though not necessarily special, worlds. What Webb brought to the table was sensitivity to subtle molecular fingerprints, the faint signatures of chemicals that absorb and emit light at specific infrared wavelengths. When its instruments dissected the starlight passing through this planet's atmosphere, something unexpected appeared in the data, a possible signal from dimethyl sulfide, DMS, a molecule that, on Earth, is produced almost exclusively by living organisms, particularly marine plankton. The reason that caught so much attention is simple. On our planet, there is no known non-biological process that generates large quantities of DMS. It doesn't come from volcanoes. It isn't produced by lightning. It arises from life interacting with its environment. Now, that doesn't mean DMS must always be biological everywhere in the universe. Exotic photochemical reactions in exotic atmospheres could, in principle, mimic the signal. The chemistry of alien worlds is still largely unexplored territory. But the mere possibility that a molecule so tightly associated with life on Earth might be present in the atmosphere of a planet many light years away changed the conversation. The signal was not strong enough to be called a definitive detection beyond all doubt. The uncertainties were real. Yet even a tentative indication that such a molecule might be present was enough to turn heads throughout the scientific community. What made the situation even more compelling was the broader atmospheric context. Webb also saw methane, carbon dioxide, and hints of other sulfur-bearing compounds mingling together. This mix of gases, under certain assumptions, could point toward active chemistry that is difficult to explain purely through non-biological means. The planet itself appears to be a so-called Hycean world, somewhere between a rocky super-Earth and a mini-Neptune, with a thick atmosphere and a potentially deep global ocean beneath clouds. In that scenario, you have a water-rich world bathed in starlight, with significant amounts of carbon-bearing and sulfur-bearing gases and a possible biosignature molecule in the air. Nothing in that description guarantees life, but it raises a clear, testable question, in a way no previous exoplanet observation had done. Is there a plausible, non-biological explanation for this chemical cocktail? Or does something alive have to be involved? Webb's data forced the shift from vague speculation, life might be out there somewhere, to a specific, falsifiable problem. Does this particular combination of molecules, on this particular type of planet, admit a natural explanation without biology? If the answer is yes, then a new branch of atmospheric chemistry will be born. If the answer is no, then humanity will have to confront the possibility that life is not unique to Earth. Even as that debate unfolded, Webb was still pushing the observational frontier farther back in time. It helped confirm galaxies with record-breaking redshifts, objects whose light left them when the universe was less than 300 million years old. These systems were not majestic spirals like the Milky Way. They were small, compact, and bursting with star formation. Yet the fact that they existed at all, and in such numbers, meant that the cosmic dark ages ended more abruptly than many models suggested. The telescope's deep imagery began to knit together the first coherent view of the era when the universe transitioned from opaque to transparent, when the first stars and galaxies carved out bubbles of ionized gas in a fog of neutral hydrogen. Each newly identified galaxy at extreme redshift added one more point to the cosmic timeline, helping scientists refine when and how the first luminous structures flickered into existence. Then came one of the most visually arresting objects Webb has revealed so far. A pair of colliding galaxies, whose tangled arms and bridges of gas formed a shape eerily reminiscent of the infinity symbol. Two galactic cores on a collision course, twisting around each other in a gravitational ballet that had been unfolding for billions of years. The image captured the public's imagination almost immediately, but, as usual, the real story ran deeper than the aesthetic. At the heart of that chaotic interaction, where the two galaxies' central regions were plowing through dense gas and dust, astronomers found evidence of a supermassive black hole in the process of rapidly feeding. Its energy output, the density of its surroundings, and the violent conditions of the collision pointed toward a possibility that has long been considered rare but crucial: a direct collapse or rapidly assembled black hole in the middle of an ongoing merger. In other words, the infinity-shaped system wasn't just a pretty picture. It was a laboratory for watching, in slow motion, the growth of one of the universe's most extreme objects. By tracing how gas funneled toward the center, how star formation ignited and then was snuffed out, and how the black hole's outflows impacted the surrounding material, scientists gained a window into processes that may have been much more common in the early universe, when galaxies were smaller, closer together, and more prone to violent encounters. Meanwhile, Webb continued to make quiet but profound advances in another area, actually seeing planets in other solar systems. For decades, exoplanet detection relied heavily on indirect methods, inferring the presence of worlds from tiny dips in starlight or subtle shifts in stellar motion. It worked, and it revealed thousands of planets. But it always felt a bit like trying to reconstruct a landscape from shadows on a wall. That's why capturing a direct infrared image of a distant planet, separating its light from the glare of its star, marked such a turning point. Using a specialized device to block out the star's overwhelming brilliance, Webb isolated the faint glow of a massive gas giant orbiting far from its host. For the first time in space-based observations, astronomers could analyze the planet's own light with the kind of sensitivity usually reserved for stars and galaxies. From that light, they could extract temperature, atmospheric composition, and hints about cloud layers and haze. Methane, water vapor, and other molecules left their fingerprints on the spectrum. What had once been a line in a catalog planet X, mass Y, distance Z, suddenly became a real world with its own weather, its own structure, its own character. Direct imaging like this is easiest for big, hot, widely separated planets. But it is also a proof of concept. If Webb can cleanly separate and analyze the light from such worlds, then future telescopes built with even more advanced coronagraphs or star shades could do the same for smaller and cooler planets, the kind that might more closely resemble Earth. In that sense, Webb's first exoplanet portraits are like the early photographs of distant galaxies, crude by future standards, but revolutionary in their moment. While all of this was happening, while Webb was catching hints of possible biosignatures, watching black holes grow, and resolving galaxies at the edge of time, it also demonstrated an unexpected strength closer to home, tracking small, fast-moving objects in our own celestial neighborhood. Near-Earth asteroids are notoriously difficult to study in detail. They're dim, move quickly across the sky, and often slip past with only a brief window of observability. Yet Webb has managed to lock onto several of these objects, analyzing their thermal emission and reflected light to determine their sizes, compositions, and orbits with high precision. In some cases, this information refines estimates of impact risk, not necessarily for Earth, but even for the Moon or other bodies whose gravitational fields can subtly alter asteroid trajectories. None of these targets are as glamorous as a galaxy at redshift 14 or a possible life-bearing exoplanet. But they matter in a different way. They anchor our cosmic ambitions to something immediate and practical. Understanding the debris that shares our region of space. Taken together, all of these threads, early galaxies growing at breakneck speed, black holes appearing before they should, galaxies going silent almost as soon as they wake up, strange chemical fingerprints on distant worlds, and detailed views of both the farthest and nearest objects, paint a picture of a universe that is anything but calm. It is restless, dynamic, and often at odds with the clean, orderly narratives that once seemed adequate. And that, more than any individual discovery, may be the most disturbing and exhilarating thing James Webb has shown us so far. The universe is not behaving like a carefully plotted story. It is louder, faster, and more surprising than the models we use to comfort ourselves with. The telescope wasn't launched to make us feel better about our theories. It was launched to test them. And so far, the universe is winning. By now, it should be abundantly clear that James Webb is not simply another space telescope. It isn't Hubble's successor in the sense of doing the same job with slightly better resolution. It isn't just a bigger mirror floating in a different orbit. It is something fundamentally different. A tool that is quietly reshaping the entire framework through which astronomers interpret the cosmos, not through sensational headlines or theatrical announcements, but by accumulating the kind of precise, unyielding data that makes old assumptions impossible to sustain. That transformation doesn't always announce itself loudly. Most of the time, it manifests as a subtle shift in the kinds of questions researchers are even permitted to ask. Before Webb, astronomers had educated guesses about the early universe, extrapolations built on limited data and reasonable-sounding models. Now, they have measurements. Before Webb, scientists could detect an exoplanet's presence and estimate its size. Now, they can describe its weather patterns, map its cloud layers, and identify specific molecules drifting through its sky. Before Webb, the assumption was that galaxies took their time assembling, slowly gathering gas and stars over hundreds of millions of years. Now, astronomers have witnessed galaxies that formed, blazed through their star-making phase, and went dark, all within the universe's first billion years. That's the real shift. Not just an expansion of what is known, but a recalibration of what is considered possible. Because what this telescope has demonstrated, over and over, is that the universe did not evolve in the slow, predictable manner that many theoretical frameworks anticipated. It evolved rapidly, and in some cases, violently. Galaxies grew faster than models predicted they could. Black holes didn't wait patiently in line for billions of years to accumulate mass. Stars formed, burned out, and seeded the next generation with heavy elements long before the cosmic calendar seemed to allow it. And yet, there they are, visible in Webb's data streams, undeniable and sharply defined. So, astronomers find themselves in an unusual position, a place where some of the most significant answers have only generated deeper, more troubling questions. Why were so many galaxies already mature when the timeline suggested they should still be assembling their first structures? How did supermassive black holes emerge so early in cosmic history? What mechanisms allowed them to feed so aggressively in such a short span of time? What kinds of worlds exist beyond our solar system that can harbor not just water and clouds, but chemical signatures previously seen only on Earth? And perhaps the most honest question of all, how much of our understanding was constructed on models that were simply too orderly, too gradual, too simplified to capture the messy, chaotic reality of cosmic evolution? Webb is not here to validate comfortable narratives. It is here to challenge them, to stress test them, to ensure that the theories astronomers build are not just intellectually satisfying, but grounded in observable reality. And the work is far from over. There are thousands of observations still in the pipeline, data that has been collected but not yet analyzed or released publicly. Entire surveys are planned to run for years, gradually building up deeper and more comprehensive views of specific regions of sky. New instruments are being designed to complement Webb's results, to observe in different wavelengths or with higher spatial resolution, filling in gaps and cross-checking findings. Then there are the discoveries no one has imagined yet, the quiet anomalies buried in background galaxies, the strange patterns in redshift measurements that don't quite align with expectations, the peculiar atmospheric compositions on worlds that weren't supposed to have atmospheres at all, the unexplained gaps in stellar mass distributions, the gravitationally lensed flashes that might be something more than ordinary supernovae. Because the defining characteristic of a telescope like this is that you never really know what matters until you point it at something and look, and when you finally do, the result is almost never what you expected. No one anticipated that Webb would find galaxies that had already shut down their star formation before they even had a chance to mature. No one predicted that hints of possible biosignatures would appear in the atmosphere of a planet over 100 light-years away within the first few years of operation. No one foresaw the sheer level of detail that would emerge, from the most distant galaxy ever observed to the subtle cloud structures on a gas giant orbiting a nearby star. But that is exactly what has happened. Not once, not occasionally, but continuously. Observation after observation, target after target. And in doing so, Webb has quietly shifted astronomy from a field heavily reliant on hopeful estimation and statistical inference to one increasingly grounded in direct evidence, meticulous detail, and sometimes uncomfortable clarity. It is not about producing aesthetically pleasing images, though those certainly capture public attention. It is about finally seeing what is actually out there, stripped of the layers of assumption and extrapolation that were unavoidable in earlier eras. And if this is what the first 3 years have revealed, then the next decade is not just promising, it is going to fundamentally alter the way humanity understands its place in the universe. Consider what has already changed. The early universe is no longer a vague concept, a theoretical construct sketched in broad strokes. It is now a place with specific structures, specific galaxies, specific chemical compositions that can be measured and compared. Exoplanets are no longer abstract dots inferred from wobbling stars or dimming light curves. They are worlds with atmospheres that can be dissected molecule by molecule, revealing climates and chemistries that challenge every preconception about planetary diversity. Black holes, once treated as exotic curiosities tucked away in the centers of distant galaxies, are now recognized as active players in cosmic evolution from the very beginning, shaping their surroundings and growing at rates that still defy easy explanation. Even our own solar system, studied for centuries with telescopes on the ground and spacecraft sent to explore its moons and planets, continues to yield surprises under Webb's infrared gaze, water plumes on Europa, organic molecules on distant icy bodies, temperature gradients on Neptune's poles, all details that refine and sometimes upend established models. This is not incremental progress. This is a cascade of revelations that forces every subfield of astronomy to reconsider its foundations. And the uncomfortable truth is that many of those foundations are cracking. The standard models of galaxy formation, built painstakingly over decades, are struggling to account for the sheer number and maturity of early galaxies Webb has revealed. The cosmological principle, the idea that the universe is fundamentally uniform and isotropic, has been questioned by observations of possible directional spin preferences in distant galaxies. Even the expansion rate of the universe itself, a number that should be straightforward to measure, remains stubbornly uncertain, with different methods yielding conflicting results. Webb's observations of gravitationally lensed supernovae offer one more avenue to resolve that tension, but they also raise the possibility that something deeper is broken in the models, something that cannot be fixed by simply refining measurements. Then there is the question of life. For the first time in human history, astronomers are looking at actual data from the atmosphere of a planet in another solar system and asking, seriously, whether the molecules they see could have been produced by living organisms. That is not science fiction. That is not speculation. That is a legitimate scientific question being debated in peer-reviewed journals based on spectroscopic data from a real planet. Whether the signal holds up under further scrutiny, whether alternative explanations can account for it, these are open questions. But the fact that the question can even be asked, that the data exists to make it a meaningful inquiry, represents a threshold humanity has never crossed before. And it happened not because of some breakthrough in biological theory or some radical new technology, but because a telescope looked at a planet and saw something unexpected. That is what makes Webb so disruptive. It does not wait for permission. It does not confirm expectations. It simply observes with relentless precision and forces everyone to deal with the results. And those results, more often than not, do not fit neatly into existing frameworks. They spill over the edges. They demand new explanations. They open doors that were previously locked. Some of those doors lead to fascinating new territories. The possibility of life on other worlds, the mechanisms that built the first galaxies, the origins of supermassive black holes, the diversity of planetary atmospheres, the chemical history of our own solar system. Other doors lead to uncomfortable realizations that the universe is more chaotic than previously believed, that the models relied upon for decades are insufficient, that the timeline of cosmic evolution needs to be rewritten, perhaps from the ground up. But uncomfortable or not, those doors are now open, and there is no closing them. The data exists. The observations have been made. The questions have been asked. And the only path forward is to follow where the evidence leads, even if it means abandoning ideas that once seemed secure. That is the reality astronomers are living in now. A reality where the universe refuses to behave like a well-ordered textbook example, where galaxies form too fast, black holes grow too big, stars shut down too early, and distant planets show hints of molecules that should not be there, where every answer raises 3 new questions, and every new observation forces a recalibration of what seemed like settled science. And Webb is just getting started. Its instruments are still functioning perfectly, its orbit is stable, its fuel reserves, managed more efficiently than anticipated, suggest it could continue operating well beyond its original mission timeline. That means more observations, more deep fields, more exoplanet atmospheres, more lensed quasars, more early galaxies, more surprises. It also means that the cascade of discoveries, the flood of data that has already reshaped so much of astronomy, is not slowing down. If anything, it is accelerating. As more time passes, as more targets are observed, as more patterns emerge from the noise, the pressure on existing models will only intensify. Some will adapt, Some will be discarded. New ones will be proposed, tested, and either confirmed or ruled out by the next round of observations. This is how science is supposed to work, but it rarely happens this quickly or this dramatically. Webb has compressed what might have taken generations of telescopes and decades of incremental progress into a few short years of relentless revelation. And the pace shows no sign of letting up. So where does that leave us? It leaves us in a universe that is stranger, more dynamic, and more intricate than the one we thought we lived in just a few years ago. A universe where the rules are still being written, where the boundaries of the possible keep shifting, and where every new piece of data has the potential to overturn something previously thought to be solid. It leaves us with questions that matter. Questions about origins, questions about endings, questions about whether we are alone, questions about whether the laws of physics, as we currently understand them, are complete, or whether there are deeper principles waiting to be uncovered. And it leaves us with the sobering realization that for all the progress that has been made, for all the galaxies cataloged, and all the atmospheres analyzed, and all the black holes detected, humanity is still just scratching the surface. The universe is vast beyond comprehension, and Webb, for all its power, is still only seeing a tiny fraction of what is out there. But that tiny fraction has already changed everything. And as the telescope continues its work year after year, peering deeper into space and farther back in time, the changes will only grow more profound. The universe James Webb is revealing is not the one we expected. It is messier, faster, and more unsettling. But it is real, and that, in the end, is what matters most.